In the vast expanse of our solar system, Earth embarks on an annual elliptical journey around the Sun. Aphelion marks the point in this cosmic dance where Earth reaches its farthest distance from the Sun. The word itself hints at this celestial separation, derived from the Greek words apo, meaning away, and helios, meaning sun. Imagine Earth's orbit not as a perfect circle but as a gentle oval, stretched slightly at its edges. As Earth traverses this elliptical path, its distance from the Sun constantly shifts, creating points of closest and farthest approach. Aphelion signifies the moment when Earth is at the apex of this celestial stretch, marking the farthest point in its yearly voyage. Every planet in our solar system, bound by the Sun's gravitational embrace, follows its own elliptical path, experiencing its own version of aphelion and perihelion, the point of closest approach to the Sun. Understanding aphelion offers a glimpse into the intricate workings of our solar system, highlighting the dynamic relationship between Earth and the Sun. The planets of our solar system are engaged in a perpetual cosmic ballet, each tracing an elliptical path around the Sun. This elliptical motion, a defining characteristic of planetary orbits, stems from the interplay of gravity and the initial velocities of celestial objects. When a planet forms, it inherits a certain velocity from the swirling cloud of gas and dust from which it emerged. This initial velocity, combined with the Sun's powerful gravitational pull, dictates the planet's orbital path. If a planet were to move slowly, it would be pulled directly into the Sun's fiery embrace. Conversely, if it were to move too fast, it would escape the Sun's gravitational grasp altogether, hurtling off into the vastness of space. The elliptical shape of planetary orbits arises from the delicate balance struck between these two opposing forces. This continuous interplay of gravity and velocity ensures that planets are forever bound to the Sun, their elliptical orbits a testament to the elegant laws of physics that govern our universe. Earth's annual journey around the Sun reaches its farthest point in early July, marking our planet's aphelion. At this moment, approximately 94.5 million miles separate us from our star, a distance about 3.2 million miles farther than when we're at perihelion in early January. While this distance might seem significant, it has a surprisingly small impact on our planet's temperature. Contrary to what one might expect, Earth experiences summer in the northern hemisphere during aphelion. This counterintuitive phenomenon arises from the fact that seasons are dictated not by our distance from the Sun, but by the tilt of Earth's axis. During summer in the northern hemisphere, Earth's axis is tilted towards the Sun, resulting in longer days and more direct sunlight. This increased exposure to solar radiation leads to warmer temperatures, even though we're farther away from the Sun. Many people mistakenly believe that Earth's distance from the Sun dictates the changing seasons. It's a logical assumption, but one that overlooks a critical factor: the tilt of Earth's axis. While it's true that Earth's elliptical orbit brings us closer to and farther from the Sun at different points in the year, this distance variation has a relatively minor impact on our planet's temperature compared to the influence of axial tilt. Imagine Earth spinning on its axis like a top. This axis isn't perfectly upright, but is tilted at an angle of approximately 23.5 degrees. This tilt remains constant as Earth orbits the Sun, but its orientation relative to the Sun changes throughout the year. During summer in the northern hemisphere, the North Pole is tilted towards the Sun, resulting in longer days and more direct sunlight. Conversely, during winter in the northern hemisphere, the North Pole is tilted away from the Sun, resulting in shorter days and less direct sunlight. Aphelion isn't a phenomenon unique to Earth. Every planet in our solar system, bound by the Sun's gravitational pull, follows its own elliptical path, experiencing its own aphelion and perihelion. These points of farthest and closest approach to the Sun vary greatly depending on the size and shape of a planet's orbit. Consider Mars, our rusty red neighbor. Mars's orbit is significantly more elliptical than Earth's, resulting in a more pronounced difference between its aphelion and perihelion distances. At aphelion, Mars is approximately 154 million miles from the Sun, while at perihelion, it's just 128 million miles away. This significant difference in distance has a noticeable impact on Mars's climate, leading to more extreme temperature swings between its seasons. The elliptical nature of planetary orbits and the concept of aphelion are intricately linked to Johannes Kepler's laws of planetary motion. In the early 17th century, Kepler, a German astronomer, revolutionized our understanding of the solar system by proposing three fundamental laws that govern the motion of planets. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one of the two foci. This law shattered the long-held belief that planets followed perfectly circular paths, paving the way for a more accurate model of the solar system. His second law, the law of equal areas, describes the speed at which planets travel along their elliptical orbits. It states that a line connecting a planet to the Sun sweeps out equal areas in equal times. This means that planets move faster when they are closer to the Sun and slower when they are farther away. Section 7. Kepler's Legacy, Unraveling the Cosmos. Johannes Kepler's contributions to astronomy extend far beyond his three laws of planetary motion. His meticulous observations, innovative use of mathematics, and relentless pursuit of scientific truth helped to usher in a new era of astronomical understanding. Born in 1571 in Wilderstadt, Germany, Kepler's fascination with the cosmos began at an early age. He studied at the University of Tübingen, where he was introduced to the heliocentric model of the solar system proposed by Nicholas Copernicus. This model, which placed the Sun at the center of the solar system, would have a profound impact on Kepler's future work. In 1600, Kepler became an assistant to Tycho Brahe, a renowned Danish astronomer known for his precise astronomical observations. Brahe's extensive data on the motion of Mars provided Kepler with the foundation for his groundbreaking discoveries. Section 8. A Dance of Gravity, the Sun's Pull. The elliptical orbits of planets and the phenomenon of aphelion are a testament to the invisible force that governs the cosmos' gravity. This fundamental force, described by Isaac Newton's law of universal gravitation, dictates that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. In our solar system, the Sun's immense mass, over 333,000 times that of Earth, exerts a powerful gravitational pull on all the planets, holding them in orbit. This gravitational force is not constant but varies with distance. The closer an object is to the Sun, the stronger the gravitational pull it experiences. As a planet approaches the Sun in its elliptical orbit, the Sun's gravitational pull increases, causing the planet to accelerate. This acceleration reaches its maximum at perihelion, the planet's closest point to the Sun. Section 9. Aphelion Significance, a Cosmic Perspective. While aphelion might seem like an obscure astronomical term, it holds a significant place in our understanding of the cosmos. It serves as a reminder of the dynamic nature of planetary orbits, the intricate interplay of gravity and velocity, and the profound influence of the Sun's massive presence. Studying aphelion and perihelion provides valuable insights into the orbital mechanics of celestial objects, not just in our solar system, but also in distant star systems. By observing the subtle variations in a star's light as a planet passes in front of it, astronomers can infer the shape of the planet's orbit and determine its aphelion and perihelion distances. This information can shed light on the planet's formation, composition, and potential habitability. Moreover, understanding aphelion is crucial for planning space missions. Section 10. Conclusion. Our place in the Grand Ballet. As we contemplate Earth's aphelion, we gain a deeper appreciation for the intricate celestial dance that governs our planet's journey through space. We are reminded that our seemingly static world is in constant motion, bound to the Sun by the invisible force of gravity. The elliptical nature of Earth's orbit, a characteristic shared by all planets in our solar system, is a testament to the elegant laws of physics that govern the cosmos. Aphelion, the point of our farthest distance from the Sun, highlights the dynamic interplay of gravity and velocity that shapes our planet's celestial path. Understanding these celestial phenomena allows us to appreciate the delicate balance that sustains life on our planet. The slight variations in Earth's distance from the Sun, while not the primary driver of our seasons, do influence the length of our year and the subtle variations in solar energy we receive.